Swayam Prabha. Digital India. Educated India.
Today I want us to touch on a few topics that are some further details of column design. And so the first topic, basically I'll show you what in the US standards, where we tend to write out every detail of, all right, we're assuming that you don't remember from school how to calculate the elastic buckling load of something. So here's the equation, okay? And again, I gathered from reviewing the Indian code that the column provisions there focus mainly on flexural buckling, but in a broader context, there's other buckling modes that can be more critical. So let's talk about it and kind of understand where that is. Yeah, so the obvious ones, which I'm sure you're familiar with, are you can have flexural buckling about either of the principal axes. We call those X for major axis, Y for minor axis in the American code. But the one that is less familiar is if you have a doubly symmetric section, it can potentially buckle by twisting about its longitudinal axis. And so we'll look at when that may be important and how can we calculate it. Now, if it's a singly symmetric section, for instance, if it's an I section with different size flanges, maybe a 3-plate welded section, different size flanges, then the modes of failure, if it tends to be critical so that it would buckle in major axis bending, then it's essentially the same equation, the Euler equation, pi squared EI over KL squared, or the stress pi squared E divided by KL over R squared. The bending stays in the plane of symmetry. However, because of the single symmetry and the fact that the shear center and the centroid of the cross section are not at the same position anymore, if it tends to be critical by buckling about the weak axis in flexure, you can't get just buckling about the weak axis. You would always also tend to get twisting along with the buckling. Unless you were to somehow be able to rig some type of bracing to prevent the twist, then you would get the flexural buckling load or stress, FEY. But then you'd have to be holding it. Now, the holding it in that case would make it stronger. If we're not doing that, that would be rather elaborate to be able to do that. Then when it buckles by flexing and twisting, it's a smaller stress than what we would have by just flexural buckling about the minor axis, the y-axis. Then if it's an unsymmetric section, so probably the best example, just completely unsymmetric, best example would be a single angle section with unequal length legs, right? So in that case, if you say, well, how do I calculate the elastic buckling load of that? You have a cubic equation to solve in order to get your column buckling stress. And then lastly, possibly one of the calculations that's least familiar is what we call constrained axis torsional buckling. And this mode of buckling often happens when we have, say for instance, metal buildings or any buildings where maybe you have possibly a window wall and you have columns that are supporting the structure of that window wall, and you can brace one flange of the column there within the plane of the wall, but you don't have bracing to the other flange that's offset from the wall. So in that case, well, you're preventing lateral displacement at the axis where you're attaching to bracing within the wall. And if the section wants to buckle in the direction along the wall, it's going to buckle by wants to flex, but then you have a constraint at the wall, it's going to tend to twist about where it's connected to the wall. So that's a constrained axis torsional buckling. You could potentially also have a twist restraint there where you're connecting to things at the wall, but common practice is we don't count on that. And one of the reasons for that is even if you have twist restraint from whatever you're attaching the flange to, when it wants to buckle, you can get a distortion of the web that kind of removes any enhancement that you might get by restraining the twist. And so the simpler calculation is just to say, okay, we're preventing translation in the weak axis bending direction where it's connected to the wall. And so at that flange, so now we're going to tend to twist about the connection to the wall when it buckles. That's constrained axis torsional buckling. So here are the obvious equations for flexural buckling. So this is all in section E3 of the AISC 360 standard. Here's the equation for torsional buckling. That shows up in section E4 of the standard. Now, what I found, we could go into theory of elastic stability and deriving these various equations, but we're not. That's not the purpose of this class. From a designer's perspective, I think it's helpful to simply say, okay, so this is what you get. What are the terms in the equation that are contributing to strength? So if we look at what we've got here, we've got a term ECW. C sub W is the way what we write for the warping constant. I think you might write it in the Indian code as I sub W. Is that correct? And so again, that's the basically rigidity associated with that cross bending of the flanges we were talking about briefly yesterday. And then we have a length KLZ, or the spec now right side is LCZ. Basically, see, you have LCX, LCY, LCZ in the AISC standard, subscript CX, CY, or CZ. And that's just a simplified way that AISC is using. Say, well, that's your effective length, whatever it is, a K times an L for any of those axes. So the KLZ here, you can interpret that if it's a case like you see here at the bottom of the slide. That would we say is a torsionally simply supported end condition. It's free to warp. The flanges are free to warp at the ends, you can see in that sketch. Or you can say each of the flanges here, one bends like a simply supported beam in one direction, the other one bends like a simply supported beam in the other. So in that particular case, we'd say, okay, well, the KZ that goes with it, this LZ, would be 1, and so KLZ is basically the distance between those locations. What are those locations? Those are the points where we're preventing twist. So typically we just say, oh, we're going to take a K equals 1 for torsional buckling, and well, what is the unbraced length between the points where we're preventing twist? Now, if you had a situation where you have a detail that would tend to restrain or actually prevent warping at the locations where you're preventing twist, you could use, in that case, a KZ with your LZ of 0.5. But to get that, you would have to box in the ends. That would be one way to do it, is you could fabricate plates and weld them on the sides of the section to restrain that warping. Well, that'd be rather expensive to try to put in that material in order to just gain some warping restraint. So that's how that first term is working. And if you look at typical values that we get for I-section members, that's going to be the dominant term here. The other term is GJ. Well, that's your shear modulus times your St. Venant torsion constant. Maybe the Indian code, does that call it I sub T? Is that right, for the torsion constant? Okay, great, thank you. So that's what is coming in there. And then we had a divided by IX plus IY outside the bracket. If we wanted the axial force corresponding to torsional buckling, of course, we would multiply by the gross area. And then you would have an area over IX plus IY. Well, that's actually the what we call the polar radius of gyration, R0, in this case, squared. All right? So that's torsional buckling. Now, so when do we need to bother with this? Even if you look at the design aids with the American specifications, there's a lot of very useful tables for column capacity where you can look up the strengths, but they're all geared to flexural buckling. There's not a word anywhere in there about torsional buckling in those design aids. But torsional buckling is something that you could have trouble with sometimes. The mantra is that if you have KLZ that's larger than KLY, you better check it. If KLZ is equal to KLY or somehow less than KLY, you don't need to bother. So how can we have KLZ greater than KLY? Let's suppose we have a situation and we want to brace against weak axis buckling at the mid-length that you see here in the sketch below. And so we're just going to attach some rod bracing into the center of the web to provide that lateral bracing. Well, that rod bracing, if we rig it properly, would restrain lateral movement. But if that's your detail, you're just doing oftentimes we call it in the U.S., I don't know if the name is familiar here or not, but we'd have an attachment to the web of what's called a hillside washer. Okay, is that familiar here? Okay. If you're doing that, that detail is really not going to restrain twist there at the middle, all right? So in that case, you'd say, oh, now my KLY is 1/2 of the total length that we're looking at here in the sketch, but my KLZ is the total length, it's larger. And there's a good chance in that case that the torsional buckling may give you the smaller FE for your column capacity. So that would be the type of situation where we have to attend to torsional buckling. And this is just a slide to illustrate if we do some parameter studies and if we kind of play with all the various dimensions to get a feel for what's the worst case situation in terms of when we might have a torsional buckling issue if KLZ is equal to KLY. What you will find is if we assume that we're not going to have an I section with flanges wider than the section is deep, so the height of the web to width of the flange equal to 1, say, and if we have rather thin flanges, so B over T of the flanges of 24, and then we have a quite thin web, an H over TW of 192, that's kind of pushing about as far as you might go in terms of thinness. And if you're welding that, you've got a thickness of web to thickness of flange of 8, and so the guy in the fab shop may be saying, okay, I'm going to have a hard time controlling distortion when I weld that, but okay. And let's say it's a high-strength steel, so it's basically 690 megapascals yield strength, 100 KSI. That, if you put all those parameters together, you get something that's a representative worst case in terms of what would I get a reduction because of torsional buckling. And what you find if you do the calculations for that case, once you finally have so you're going to, probably a good segue to say, where do we use this? We're talking entirely about getting elastic buckling stresses right now, but what do we do with them? Once you have a controlling capital FE, which is your elastic buckling stress, that feeds into the normalized or non-dimensional slenderness for getting your column strength, or in AISC, since we don't like Greek symbols in the U.S., we put it into the Fy over Fe in the column strength formula. Okay? So if we feed all that in and we calculate a PNZ for the torsional buckling from the column strength formula, we compare that to PNY, we would get 0.974. Okay, so it is a little bit smaller than what we'd have from PNY. And that's going to happen at a very specific KL over R about the weak axis. Is basically you get that worst case, or the smallest PNZ over PNY at KLY over RY of 37. That's for KLZ equal to KLY. Well, that's getting awfully close to 1. The consideration of end restraints effects really is nowhere near that precise. PNZ over PNY increases very quickly with increases in H over BF if you are looking at other sections. So as a practical matter, that's basically the argument where the commentary of the ISC standard says if KLZ is less than or equal to KLY, you don't have to, if less than or equal to KLY, then you don't have to consider torsional buckling. Just stick with torsional buckling, with flexural buckling in a doubly symmetric section. All right, if we have a singly symmetric section, we need to calculate the buckling stress for torsional flexible. Go ahead, yes.
I have a question about that J term.
Okay, sure. Here?
Back one slide back, here. There is a confusion between the J and Ix plus Iy term. Normally J we refer as, in the elementary solid mechanics, we call that as polar moment of inertia for solid circular cross sections. And then when we come here, we say Ix plus Iy is another term which is torsional constant.
Right, okay. So so you understand C sub W, we're good there, right?
Yes, yes.
Okay, yeah, and I think that's what you call I sub W in the Indian standard. So J, I think that's IT, I subscript T in the Indian standard.
Ix plus Iy is IT. No, J is IT.
J is IT, I think.
J is IT, okay,
Okay, so that a very simple calculation of that, engineers will often sum the width times thickness cubed over 3 of all the plates in the cross section. Okay, so that's your J.
But
and that tends to be a fairly small number, relatively speaking.
But when we evaluate for solid circular sections, we use the term Ix plus Iy there. G plus polar moment of inertia, that we define as Ix plus
so
Iy.
the Ix plus Iy here is showing up in the proper place here. And again, as I'd mentioned, that if we multiply this by the gross area, then we've got the torsional buckling load, and area over Ix plus Iy is the polar radius of gyration of the section. We often write that as R naught in the American specification squared.
So the confusion arises because of this. Here J term is something different, and in circular we call that J term as the polar moment of inertia.
Right.
Circular.
Yeah, it's not the polar. J is not the polar moment of inertia.
Right.
It's the St. Bernard torsion or uniform torsion constant.
We start the derivation from circular and then we deviate here, so it becomes a confusion.
Right. Yeah. For a circular section, yeah, J is even there is it's not the let's see. Okay. Yeah. There it is. The polar moment of inertia.
For circular.
Yeah. Go ahead.
I was saying only for a circular section, the J works out to be the same as
the polar moment of inertia.
It's not true
right.
for any other section.
Yeah, but it's not. That's not what it is here. Yeah, for an thin-walled open section, again, if you assume that the widths of all the plates is fairly large compared to the thickness, it's the sum of the width times thickness cubed over 3. Okay, and again, that's a very small number, and so you're not really getting you're not really getting very much from that constant. Most of your strength is coming from the ECW, the warping constant. So here with torsional flexural buckling, again, I think, if we were in a theory of elastic stability class, we could derive these equations, but we're not, and so we can look at them and again try to understand, what are the equations telling us, right? And if you basically take these equations, manipulate with them, play with them, you can see there is the FEZ term that looks a bit like what we just were defining for the doubly symmetric section, but here we'll actually call it R naught bar squared here. That's your polar moment of inertia for the singly symmetric section. And the equation E49 is the equation for that below. So it's also dependent on the offset of the shear center from the centroid, X naught and Y naught. So that's the torsional term. We also have the FEY that's showing up there. It's kind of hard to glean it out from the equation just looking at the equations, but if we start putting numbers in for the equations, what we find is that FE torsional flexural generally is going to be something smaller than both FEY and FEZ. And you can think about that conceptually, and similar to what I mentioned earlier. If you say somehow could put rigging around the member to prevent twist, then it would just buckle by flexural buckling. Your buckling stress would be FEY. And if you could somehow put rigging around the member that restrained flexure but didn't restrain twist, it would buckle at the stress FEZ. And so if we're not putting in those constraints, it buckles at a smaller stress. So I think it's useful to be clear what are we talking about? What does torsional flexural buckling look like? We talked about the stiffness contributions there a bit. Again, you can see there's going to be an EIY as well as an ECW and a GJ that are showing up here in the stress terms here for the torsional flexural buckling. So one example of a singly symmetric section would be a T-section. And of course, one way the T-section could buckle would be this way. That would not be torsional flexural buckling, right? That's just a flexural buckling, and typically we say it's flexural buckling about the x-axis. For a T-section, that may or may not be the major axis of bending. It's just the axis where it's bending and staying within the plane of symmetry. But if we take this, if we've got a smallest buckling stress where it's wanting to buckle by bending out of the plane of the web, then it's not going to buckle in that way without also twisting. So that's our torsional flexural buckling. In U.S. practice, at least, engineers, many industry folks, particularly the joist manufacturers, like to say, oh, come on, do I really have to calculate a torsional flexural buckling load? Can I just please calculate the capacity based on weak axis flexural buckling? Okay, well, if it's an I section, when might we be able to get away with that? And so a simple rule of thumb is if you have equal width of your flanges in an I section, although a section like that is often easiest to handle in erection, in fabrication, or what have you. But one of the flanges is thicker than the other. So if your ratio of the flange thickness is between 2/3 and 3/2, then your torsional flexural buckling stress, FETF, will not be smaller than about 4% less than just FEY. So okay, just calculate it by FEY. But if you have unequal width, forget it. you better calculate the torsional flexural buckling stress. And so that would be a kind of a practical recommendation for engineering or industry folk who would like to not have to bother with running the calculations via the torsional flexural buckling formula. Just work with flexural buckling. Okay, here's the nice one, the constrained axis torsional buckling. Now if you dig into the PDF of the AISC 360 specification that we put on the Google Drive, there are equations in section E4 for constrained axis torsional buckling of doubly symmetric shapes. The case here is covered in that section E4, again for a doubly symmetric section where the example here is you've got a main frame member, say of a metal building, and you have clips that are attaching that member to a purlin or a girt on the roof or on the outside wall of the building. And so we say, okay, if we're counting on that wall or the roof diaphragm for lateral bracing, then we're preventing lateral displacement essentially there at the level of the flange that's attached to the girt or purlin. However, it's potentially we could have flange diagonals that frame from the girt or purlin and then provide bracing to the other flange. But those are expensive. Again, one process that metal building manufacturers often do, they call it essentially a bracing diagonal reduction stage. It's very common for many of the manufacturers to design the frame as if every purlin and every girt location is braced, unless there's a door or something they know is not going to be there. And then they come back and they do a calculation, okay, which of these diagonals do we really not need? And they'll remove those from the design. So if you're looking at an axial compression strength, then you have locations where the purlin or girt is providing lateral bracing, but the other flange is not braced. Okay. Now the equations that are now in section E4, they look a little bit different. They apply only to a doubly symmetric section. But here, the equation that I'm showing on this slide, it applies generally to a singly symmetric I section, and this is the way the equation is written in the AISC design guide for design 25 for non-prismatic design of frames using non-prismatic members. And the reason for that is it's very common. You may have single symmetry in a metal building on the cross section, so then, okay, how do we do it for a singly symmetric section? So again, here you can see the terms showing up, ECW, EIY, GJ. So all those terms are showing up. The other way this equation works is if you somehow had a constrained axis that's way above the rooftop here, and so you're constraining somehow off of that point, it reduces to just flexural buckling about the Y, because it's no longer twisting when it buckles, right? But as that constrained axis gets closer and closer to the shear center, then you get more capacity from this equation. And I'm writing it here in terms of the load. That's just a convenient way to write it. So we divide by gross area, we have the stress.
So,
all right. Yeah.
In some metal building structures, we see these braces going from the bottom flange.
The inside flange to the girts or purlins. That's the flange diagonal bracing.
Right.
And so the intent there is to also provide lateral bracing to that inside flange.
Right, but it's also for this constrained axis.
That would not be constrained axis at that point.
That's on the beam, right?
And that way, at that point, if you're preventing lateral movement at the top and at the bottom, you're preventing lateral movement and twist.
No, because they don't go to the top flange. I've seen these details.
Oh, they
where
come into the web?
they just go from the bottom web flange junction
Right,
and they go diagonally outwards.
right.
And so they're not really bracing the compression flange over there.
The general advice is to frame that as close to the compression flange as you can. And then
Yes.
we say then your flange is
framed.
braced.
Right.
If it's framing into the web a significant distance removed from the compression flange, now you've got a situation where the web is going to distort.
Right.
And so you're starting to lose effectiveness.
Yeah, I was always curious about that detail I noticed in some places because they weren't really bracing the compression flange. And so I was just
Correct.
wondering, okay.
Yeah, if that's framed in reasonably close to the compression flange, then it's probably pretty good.
Okay. Thank you.
Yeah.
What would be the unbraced length in this torsional buckling?
Okay, so
scenario?
again, KLZ, typically the simple way we usually calculate it, if we were talking about weak axis buckling of a column and brace,
Yeah.
we often just say, oh, don't bother with the K, just use K equals 1.
Yeah.
The unbraced length is LY, that's your KLY. Same thing here. It's the distance between locations where you're preventing twist.
Okay.
And so if you have a clips to a purlin and a flange diagonal down to the inside flange at two locations, okay, those are brace points. But now they leave out the flange diagonals for several purlins in between. Okay, so your KLZ is the distances between where the flange diagonals are coming in and you're preventing twist.
Okay. And for example, as you said in your first example, like if it is against the wall, where
Right.
it is braced continuously, so what will be that LTB?
Right, we'll come back to that.
CATB, sorry.
Here it's not necessarily continuously braced if it's attached to framing members
Yes.
on the wall. If it's attached directly to a diaphragm, then yes, you could say that's continuously braced.